Hi. Hello, my name is Abhishek Shah, and today I'll be talking about autonomous cars. Before I start, I would like to thank Dr. Lazar and Dr. Zhang for being on board for this presentation today and agreeing to be the committee members. I'd like to thank my advisor, Dr. Sillens, for his constant support of my master's studies and research, as well as for his patience, inspiration, enthusiasm, and knowledge. Autonomous cars. An autonomous car is a vehicle that can perform large computations by analyzing the surroundings and making decisions in real time without requiring humans to intervene to get from point A to point B. Let's have a look at this scenario. There is a self-driven car driving in the middle lane surrounded with traffic from all sides. There is a truck in front of the self-driven car carrying a bunch of boxes, which suddenly falls off from the truck in the middle of the road. What should the self-driven car do in this scenario? Should it swerve and crash into the car in the left lane? Should it swerve and crash into the motorcyclist in the right lane? Or should it let itself crash into the boxes and put the life of the passengers in the self-driven car at risk? This is a classic example of ethical dilemma for self-driving cars. Comparing the same situation for a human-driven car with self-driven car, any reaction we may have if we were operating the same vehicle in manual mode would be perceived as simply that a reaction rather than a intentional choice. It would be an impulsive, frightened action without any deliberation or malice. Whereas for self-driven cars, it appears more like premeditated homicide if a programmer were to tell the automobile to act in the same way given circumstances it could detect in the future. Since 2014, companies thought they were set to launch their autonomous cars. However, every now and then, it's in the news that autonomous vehicles getting into accidents. Like this one case where the autonomous car assumed that the human-driven car would yield and crashed into it. In this one, the autonomous car by Uber hit a cyclist. The autonomous car initially detected the cyclist as a tree, then as a car, then as a cyclist, but ended up ignoring it as an obstacle. This Google self-driven car by Waymo took a left turn, assuming the bus in the left lane would yield for it. Image processing for recognizing environmental situation is the most time-consuming part of the processing for autonomous navigation. It requires a huge amount of sensory data to be processed in real time. This study from 2001 uses two approaches: the reduction of the image processing load of the fast Fourier transform picture compression technique in the manner of human-eye sensitivity and simplified driving rules extracted from human driving behavior correspond to the minimum energy efficient control. One of the key strategies is to trim unnecessary data, which is possible by identifying certain regions that are more significant in particular circumstances, just like humans' perception. Perception is based on how humans interpret their five basic senses, that is sight, sound, touch, taste, and smell. The objective is to enable computers to have the perception of humans. Among all the senses, vision is considered the most important sense. To convey the sense of vision to the computers, human perception of object detection is required. Therefore, the topic for my thesis is driver's visual focus areas on complex road networks in strategic circumstances. It is an experimental analysis that uses a simulator for drivers to drive in the simulation and tracks their visual focus areas using an eye tracking device. The paper starts with introducing the problem and its importance, followed by providing a brief analysis on previous works in this area of research. In the third part, it provides the information on the equipment and the software that was used in the experiment, followed by overviewing each scenario that were designed to test the drivers. And lastly, it reveals the outcome of the experiment. The introduction is divided into three parts. First, provides an overview of the previous study on this topic by one of the previous students, Jacob Mauk, followed by questions that this study aims to discover and sharing the objectives of the study. The topic for previous work published in 2020 by Jacob Mauk was eye tracker analysis of driver visual focus areas at simulated intersection. Mauk aimed to discover where does a driver tend to focus most of their attention towards while driving. And are human drivers' habits an ideal model for a self-driven car to follow regarding the observations they make while driving? He found that the drivers spent vast majority of time focusing directly on the road in front of them when compared to the time they spent on observing the potential distractions. Mauk stated, no work is established or executed perfectly, and there are always ways to improve the quality. He suggested some future works that included diverse scenarios, such as turning at an intersection, larger sample size, and elimination of biasness. My study aims to discover these three questions. Does driving behind another car brings any changes in the visual focus areas of the driver? Are there any dissimilarities in the attentiveness of drivers while driving on a non-familiar road versus a familiar road? And in terms of the assessments a self-driving car makes while on the road, are human drivers still behaviors the best one to emulate? The objective of this study is to gather data of visual focus areas of the drivers while driving and analyze the information, which will help analysts to train the model more accurately and to improve the decision making of the model so they perform more educatively, confidently, and are more aware of their surroundings while on road, and to suggest possible implication of this data in public safety, automotive engineering, and artificial intelligence to fuse it with devices and algorithms in future. The next section will be going over the evolution of eye tracking technology and the mechanism of autonomous vehicles. Eye tracking is the process of measuring either the point of gaze or the motion of an eye relative to the head. This study uses eye tracking technology to evaluate the attentiveness of drivers. Therefore, it is essential to understand the development and application of eye tracking technology. Since 1879, tons of papers have been published on how us humans gaze at while reading. Initially, eye movements were observed by post-test survey. This was changed over the years as new instruments were brought in use by researchers. In 1900s, scientists used light beams that were reflected off the subject's eyes and subsequently recorded on film. By 1980s, computers became a means of monitoring users' responses to material like animated graphics and online adverts, since they were strong enough to handle visual tracking data in real time. Moving to the next part, autonomous vehicles use sensors, actuators, sophisticated algorithms, machine learning systems, and potent CPUs to run the software. The software commands the vehicle to manage acceleration, braking, and steering. A single self-driving car is predicted to be able to gather up to 1 gigabytes of data each second. Autonomous vehicle must be fitted with a platform that produces at least 75 tera operations per second of computations for every watt of power used to minimize human error. Some major challenges by self-driving cars are creating and maintaining maps, social interactions while driving, tackling bad weather, and ethical dilemmas. Capturing massive amounts of data with the help of the simulator and applying it to the algorithms can help tackle the challenges. To gather data, simulators are used, which allows researchers to test in a controlled environment. To train autonomous vehicles in a physical environment with sensors and eye tracking devices can be dangerous. The purpose of the simulator emulates real world driving and gather vast amount of data. The next section, we will go over the setup that was used to conduct the experiment. The experiment used an eye tracking device mounted on a driving simulator and a simulation software built on Unity 3D game engine. The eye tracker device sends out near infrared light. The light is reflected in participants' eyes. Those reflections are picked up by the eye tracker's cameras. Through filtering and calculations, the eye tracker knows where you are looking. The visual focus of the drivers are indicated by the use of heat maps and fixation maps. The heat map displays the relative intensity of values captured by your eye tracker within each square of a grid that divides a picture, giving each value a color representation. As shown in the figure B, the heat indicates that the driver's visual focus is evenly distributed to the car in front and the traffic light followed by the yellow traffic sign. Figure C indicates how a fixation map looks. Eyes sweeping the scene during a fixation and fixate on the foveal region of our field of vision. This enables the visual system to process in-depth information about the object being viewed. The red spots in the map are the fixation points. Blue arrows are the removed eye tracking scan path, also known as saccades. The green arrow is the retained eye tracking scan path, also known as smooth pursuit, and the little red arrows are the optical flows. The driving simulator is built from three major equipment: a Logitech G920 driving kit, which includes a steering wheel, shifter, and pedals. Three Dell monitors angled at 60 degrees from the monitor in the center, and Volare chassis where the driving kit and monitors can be mounted. This is the simulator that was used for the experiment. One of the major objectives for building the new simulation was to focus more on the easy reformation of the scenarios, environments, traffics, and distractions. The simulation was built on Unity as it provides all-in-one editor, 2D and 3D support, AI pathfinding tools, rapid iterations, and has a rich asset store. The scene incorporates multiple Unity packages downloaded from Unity's asset store. These packages allow us to construct editable detailed multi-lane parametric roads, intersections, and sidewalks with this editable city designer, which operates directly within Unity's scene view. Another package from Unity allows to incorporate AI-based cars and waypoint systems. The main logic is handled by a single AI traffic controller to which AI traffic cars register. The AI traffic controller uses the C# job system and burst compiler to distribute processing across all available CPU cores, reducing usage on the main thread and enabling users to use more of one's process costing system for other content. The simulation software includes a drivable car that the user can use to maneuver through the simulation. The car uses the same AI traffic controller script, which prevents it from other cars to crash into it, along with Mauk's car controller script. The next section goes over the process that was used in the study to conduct the experiment. There were 20 participant drivers recruited via email, which had an informed consent form briefing them about the research. The requirement to qualify for the participation was to have a driving license. This would ensure that the participants are aware of the general rules and regulation of traffic. This navigation map was strategized to direct the participants' drivers through 18 intersections rigged with several distractions. The yellow arrow you see on the map was the course selected for testing the drivers. A total of 14 flashing signboards guided the participants as they drove the course. The green box in the map indicates the downtown area of the simulated city, and the blue box indicates the residential areas. The traffic light tends to change quickly in downtown areas and implies more traffic laws to test the driver's attentiveness. As you can see in the map, it incorporates three-way intersection, four-way intersection, and five-way intersections. Some of them intersections are symmetrical, where drivers seem to struggle. Before each trial began, eye movements of the participants must be calibrated. During calibration, geometric characteristics of participants' eyes are estimated as the basis for a fully customized and accurate gaze point calculation. When the green cross aligns with our pupils, it is expected to provide good accuracy and good precision. The eye tracking device used in this experiment uses two software. First, gaze point control, which calibrates the distance and eye movements of the participant by 9-point calibration system. Second, gaze point analysis, which allows us to record each trial after calibration and visualize the results using heat maps and fixation maps. There were 36 scenarios incorporated with 136 events. In this table, the active distraction column groups the vehicles that are going in each direction separately and counts them as one in each scenario. Passive distractions include stationary vehicles, idling pedestrians, rocks, and billboards. The passive distraction column groups non-moving vehicles in each area and counts them as one in each scenario. The passive distraction column also groups non-moving pedestrians idling in each area and counts them as one in each scenario. There were 41 active and 26 passive distractions, 22 traffic lights, 41 signs and road signs, and 6 passive pedestrians incorporated in 36 scenarios. The total column on the rightmost side of the table indicates the total number of events occurring in each scenario. The next 3 slides, including this, will show each scenario. I'll point out not all but some major events among these 36 scenarios. Starting with scenario 2, where pedestrian appears as soon as the driver enters the intersection. Notice that the driver is driving behind another car in some of the scene. Billboard in scenario 6, and pedestrian suddenly starts running in scenario 7. An example of a symmetric intersection in scenario 9, where driver is instructed to take sharp right at 90 degrees, and the cars in front turns along with the curve at 60 degrees, which might seem as they are turning where the driver is instructed to go. A rock in the middle of the road in scenario 10, 2 active pedestrians in scenario 15, do not enter sign at 5-way intersection in scenario 17, idling pedestrians in scenario 20, 21, 23, 24. Jaywalker appears in scenario 24. Kids skating in scenario 31, billboard across the idling pedestrian in scenario 34 and 35. Now let's talk about how the participants performed in all the scenarios. The table indicates the rate of performance of the participants, which is calculated with a simple formula. Attentiveness equals to noticed events by total events of 100%. Where noticed events are the total number of events in each category where each driver gazed, fixated, or reacted. And total events are the total number of events in each category that exists. For example, driver 1 gazed, fixated, or reacted to 23 out of 41 active distractions. Therefore, 23 divided by 41 of 100% is equal to 56% approximately. The average column indicates the average performance of each driver in all the categories, and the average row indicates the average performance of all drivers in each category. In the next slide, we will go over some common gaze patterns seen in majority of the participants throughout this experiment. One of the major findings in this study is that the drivers tend to not only focus, but also follow the cars in front of them, even if the car in front is making an unsafe move. Drivers are also found less attentive to vehicles on the left lane. Distractions noticed from a distance draws drivers' major attention, and hence the drivers lack to react to any other object that may appear in the scene before the distractions in the distance. Before the skating kid appeared in the scene, the fixation map indicates that the participants' focus was sort of locked at the road sign and the cars on the other side of the intersection. It was too late before they noticed the kid. In this case, the participant is waiting behind a car at an intersection. The fixation map indicates that the participant is majorly focusing on the car in front. Even when the light turns green, the participant does not visually conform. Instead, they just assume that the light must be green because the car in front just has started driving. Also, the participants did not notice that the light turned yellow when they were entering the intersection. In the top video, the car in front of participants is approaching the rock and is programmed to swerve right and drive over the sidewalk. This approach is unsafe. However, in the bottom video, the car in front has already reached the intersection. The participant did not notice if the car ahead passed the rock from right or left. This time, the participant passes the rock from left lane. There were 2 billboards installed in the entire course, one at the entrance of a turn and another at an exit of a turn. The heat map in the top image indicates that the driver is distracted by the billboard and does not notice the pedestrian idling on the right side of the road. The heat map in the bottom image indicates that the driver is currently distracted from the road. We will talk more about this scenario in the next slide. Let's observe the heat map patterns in this scenario first. As you may have noticed, in this scenario, the participant faces a chain of events caused by their own errors. First, driver majorly focuses on the car in front, does not visually confirm if the light was green. Driver does not notice the light turned yellow by the time they enter the intersection. Second, driver does notice the yellow flashing sign that indicated the driver to turn right, and the driver did change the lanes. Third, driver gets distracted by the billboard. Fourth, driver notices the speed limit sign too late and moves their eyes off the road to look at their current speed. Fifth, a man starts running across the road while driver's focus is at the current speed. And by the time the driver understands the situation, it's too late. The heat map in these two videos indicates the eye movement patterns of participants who stopped on the right side video and the one who did not stop for the pedestrian on the left side video. Only 7 out of 20 drivers noticed early and yielded for the 3 jaywalkers and 3 pedestrians that were incorporated in the entire course. The rest either dodged them or were too fast to even realize they had hit a pedestrian. Let's observe the heat maps in these two scenarios first. As you may have noticed, in these two scenarios, traffic lights were placed too close to the crosswalk. A stop sign was placed before those intersections, which indicated the point where drivers should stop, or else the traffic light would not be visible. Only 10% of the drivers stopped at the stop sign before the traffic light. Drivers' visual focus areas while turning in an intersection was one of the future aspects of this study that Mauk suggested. It was found that majority of drivers' focus is concentrated on the edge of the side where they are about to turn. It was also seen that 50% of drivers waited on the light to turn green, where it was legal to make a right turn on red. Out of 18 intersections, 9 were three-way, 7 were four-way, and 2 were five-way intersections. Participant drivers seemed to struggle at intersections in scenarios 9, 14, 16, 30, and 32, among which 9, 14, and 30 were asymmetric three-way intersections, and scenarios 16 and 32 were five-way intersections. In scenario 9, drivers were directed to take a 90-degree right turn, but 30% of the driver instead followed the car in front that was following the road that curved 60 degrees to the right at a three-way intersection. 4 out of 20 drivers turned right at this no turn on red intersection. In scenario 14, 5 drivers at this intersection followed the car in front and did not stop for the two pedestrians who appeared on the crosswalk. In scenario 16, drivers struggled and made some minor mistakes, such as waiting for the light when right turn on red was legal, focusing on the edge of the road while turning. 50% of the driver did not notice the do not enter sign and stopped in the middle of the intersection to figure out which right turn to take. In scenario 30, 20% of drivers struggled to understand which right lane to turn, the 90-degree or 120-degree. They instead followed the car in front. It has been noticed that the drivers in unfamiliar scenarios tend to follow the car in front of them more often. In scenario 32, driver's visual span was widest at this intersection. To answer the second question that was proposed to discover, previous studies have claimed that drivers are more likely to be involved in accidents while driving on a familiar road. Therefore, participants were asked to drive the simulator for the second time. Scenarios in both the trials were same besides few minor changes in traffic. The purpose of having the participants drive the simulation twice was to learn if there are any changes in human driving behavior when they drive on a familiar road when compared to driving on a non-familiar road. Drivers were more at ease and comfortable while driving the second time. As the heat maps in both the pictures indicate, the claims from previous studies seem to be accurate as the attentiveness and visual span of the participant drivers was reduced in comparison to their first trial. Their fixation on strategic points was too brief for them to react in case of an unprecedented event. It was also found that the participant did not follow the car in front and made unsafe move as much as they did in their first trial. To answer the third question, the human brain is subjective and depicts the existence of a being in conjunction with others, whose identity reflects a dynamically engaged reality. Hence, even though human drivers' behaviors may not be the most appropriate ones to emulate for an autonomous vehicle, they are essential for machines to have the perception of humans. Based on the results we achieved, some conclusions were drawn. The results have shown that the drivers are more attentive in busy occupying scenarios. Spending most of the time focused on the empty road straight in front of the driver could not be considered safe, could be considered safer than spending the majority of time focusing on the car in front. Drivers lack both visual acuity and awareness when taking turns as their visual span shrinks. Human drivers become careless and inattentive while driving a familiar road, whereas assuming the self-driven car can trim the unnecessary data and has the capability of higher computation speed, it would not let down its guard and be attentive, even if it had driven through the same area several times. There is always more we can do to make our work meaningful. With that being said, I would like to propose some future aspects of this project. Having a larger sample size would definitely help upcoming researchers identify outliers in data and provide smaller margins of error. Upgrading eye tracking devices to get data from the side to screens could help gather visual information from the side mirrors. Last but not the least, introducing drivers to ethical dilemmas such as shown in the beginning of this presentation can help algorithms reach the human perception. These are my references I used. And that's my time, and I would like to answer any questions you may have.
Okay, thank you very much. Great talk. Any questions?
Yeah, very nice presentation.
Thank you.
You mentioned that you collect, not you collected, is 1 gigabyte per second at the beginning. The image.
75 tera operations per second.
Yeah. You mentioned, is that how many? Is that 1 gigabyte per second?
Well, it can gather 1 gigabytes per second of data in one in every run.
For image data.
Yeah.
Mm. You mean that's for real or for your simulation?
No, not my simulation. A real self-driving car can gather up to 1 gigabytes of data each second. So that is really big data to compute. So that is why we are trying to emulate human perception, because when humans are driving, they only focus on relative things. They trim out the unnecessary data, but the computers yet are not able to do that. We have just reached the second level of automation out of 6 level of automation. So that's what we are trying to work on.
Does that mean the raw image or raw video?
Sorry?
Raw image, original image data.
Yeah. Yes.
Yeah, I'm pretty sure it's pre-processed.
Yeah.
There's no way they can process that amount of data.
Yeah, the whole kind of, I should jump in here. Really, this and Jacob's research was really trying to say, can we get away with, instead of gathering the entire image, gathering only parts of the image to try to improve the efficiency of the system?
Yes. Even if they gather the original image, they have to use filter to filter,
Oh, yeah,
filter out most of them.
yeah.
There's no way, unless in the future there's a super CPU can process it.
Yeah.
Yeah,
I think
99%.
there's a lot of pre-processing. I think you mentioned that at the beginning of the presentation.
Yeah, the perception, basically you only process the useful information.
Yeah,
Probably.
that's the key. What's the useful information?
Yeah, the most of them are noise, irrelevant. Yeah, that's all my question.
Thank you.
So how long did each participant drive?
The participants it took around 30 to 45 minutes, depending on how, the participants' driving behavior. Some participants were like they wanted to drive really fast, so those ones took like 30 minutes because they drove the simulation twice. And some participants were driving really slow, so it took like around 45 minutes for them.
Yeah, I wonder if people get tired.
Yeah, they did get tired after the first simulation because it kind of gives you some dizziness when all three screens are running. So I used to let them take some rest after the first trial. So when they were ready, I used to have them to drive the second time.
Interesting. And so the second question I have, I don't know if you can answer that. So is there like any open source software for like self-driving cars out there that
There is no open source softwares like specifically like if you're like I was researching on this as well. I was trying to develop for BMVs. I was looking that every year people are like BMV officers get into 3,000 accidents while going for driving tests with new drivers. So if driving simulators could emulate using the Google map, like real-time map, and they could have the new drivers to drive on the simulation instead of having them to drive in the road. That would save a lot of accidents. So there is no software yet built to incorporate real maps, but there are softwares like especially there are games, not softwares, I'd say, uh, like that can be used to do this. But I think most of the open source, like there's no so open source softwares. The research that are done are mostly by the universities or the manufacturing companies.
so it would be interesting to like compare the people's driving with like the machine driving.
Yeah.
and reactions.
Yeah.
Because like I mean this research is very interesting because it could like improve like things that the car will try to help you.
Yeah. While I was researching about this project, I also found out that there also some people are also working on autonomous police cars. So the police cars can like analyze if while tracing a criminal driving a car that based on the basis of the driving behaviors, if the the criminal is going to take a left or right, or what's going to be their next movements. So a lot of people are also working on that. So I mean, yeah, this has like a lot of potential, and like there's so many future aspects that we can work on for this research.
Okay, great.
Thank
you.
I just had a couple of things. First of all, an observation. When you were talking about five-way intersections, um, Actually, cities are trying to get rid of them. There are 2 5-way intersections in Boardman that have been closed down in the past few years. So,
Thanks.
yeah, it's definitely true that that's one of the most dangerous things out there. So,
Yeah.
yeah, it supports that. And the other question, I guess, which is sort of my bigger question is, now that you've seen how drivers' gaze tends to go during these scenarios, my original thought long ago when I started this research was that would be useful for determining what parts of the image an autonomous system should focus on. Is that the case, or is that sort of not really the case?
I mean, are you asking like if the autonomous vehicle can use the image detection?
Well, I was sort of more like saying, given where we've seen human drivers focus in these studies, should an autonomous system focus on the same areas, or should they focus elsewhere in terms of where?
Well, as far as I've researched, I've seen that drivers tend to focus like specifically when they are in, when they have to wait a longer in traffic on traffic lights, or when they get frustrated, their behaviors changes mostly at those scenarios. But for autonomous vehicles, that won't be the case. And like specifically for like I said earlier, like for trimming the unnecessary data, human perception is really necessary for autonomous vehicles. So even though like it may not be appropriate for like entire all the cases, but it is still essential to have the human, for machines to have the human perception, because the autonomous vehicles are not driving among the vehicles that are all autonomous vehicles. They are driving with the human drivers as per today's day. I mean, progress in development of autonomous vehicles.
So there's some information we can gather about what to look at based on where humans look.
Yeah.
Okay. And that's pretty much all I had. Are there any other questions? Okay. Thank you very much. Excellent.
Thank you.
Thank you.
Congratulations.
Thank you.
I think at this point, I think you email it. Do you email the thesis to the graduate office at this point?
I haven't emailed them, but they asked me to attach some other documents and email it to them before December 5th.
Okay. Yeah, I think we all get it. Everyone on the committee gets an email confirming things. So I think that's kind of our role.
All right.
Okay, so we still don't need to sign it.
I don't think so. I don't think.
In the email it said that I don't have to get it signed from the committee members and advisor yet, and I'll have to leave it blank and send it to the graduate office.
Yeah, I think we all get a confirmation email at some point.
Okay.
Okay. Thank you very much.
Thank you.
Fantastic job. I learned a lot from this, things I wasn't necessarily expecting, but that's the purpose of great research. Thank you very, very much.
Thank you so much.
Okay.
Thank you.
And I guess we're gonna sign off now.
Yeah, have a nice weekend.
Thank you.